Okay, Unit 9 today, right? In there we're going to be looking at 3 or 4 functional groups. Carboxylic acids, esters, amines, and amides. So the things that are going to be covered today. We'll start with our carboxylic acids. And as far as organic chemistry goes, carboxylic acids are as exciting as it gets, and that's not really saying too much. The carboxylic acid functional group they have a carbon double bound to an oxygen. Okay, that's our carbonyl group, right? We saw that with aldehydes, we saw that with ketones, we saw that with, oxidation of primary alcohols when we first saw the carboxylic acid functional group. So, it's got the carbonyl, which we know is polar, because oxygen and carbon have different electronegativities. There's an uneven distribution of electrons between the carbon and the oxygen. Carbon, again, has only 4 bonds, and the carboxylic acid functional group specifies what 3 of those have to be in order to be a member of that class of organic compound. Double bound to an oxygen, single bound to an OH group. Okay, that leaves only 1 bonding position left. You do see the carboxylic acid functional group written in a couple of different ways, and you need to be able to recognize those. These are all just different representations of the same functional group, carboxylic acid. Okay, when we name the carboxylic acids, we're going to drop the E from the alkane parent name, and we're going to add OIC and the word acid. OIC and the word acid. So the first member of the carboxylic acid functional group would look like this, or alternatively look like this. Same thing. I know it's starting to look a little funny, right? Notice here that I didn't put R, okay? I didn't put an R there, but a lot of books will have an R group there, meaning that that's an alkyl group. But in reality, there is a member of the carboxylic acid class that does not have an alkyl group attached there. It's the first member. Okay? Normally, we would say one carbon derivative is methane, right? We're going to drop the E and add OIC. We would call this methanoic acid. But it's not ever called that. Okay? It's got a common name, just like the first member of the aldehyde class had. This is called formic acid. Its common name. Note the similarity to the first member of the aldehyde class, which was formaldehyde. See these C1 derivatives take this form prefix, this formaldehyde. We'll see formamide for the amide, formic acid. Again, I wish I could tell you which one. And if we were having an essay type exam, then of course you could pick the one that you were most comfortable with and you could just use it. But either one could be present on the exam. Okay, so if you see this and you're thinking formic acid and you go look at choices A, B, C, and D and formic acid isn't there, it's probably your first indication that I'm not wrong. Don't think you're wrong right off the bat to say, well, maybe it's a different name. So let me take a quick look at the methane derivative, the IUPAC methane member. The C2 notice when I say C2 and C1, I'm including the carbonyl carbon. You can't randomly just drop that thing off. Okay, this is in the carbon chain. Remember, we name our organic compounds by first determining what the longest continuous chain of carbons are. Now, once we have that longest continuous chain, we name it accordingly based on the first 10 alkanes that we memorized. This is in the carbon chain. People just seem to leave that out for some reason. I don't know why. We would say this one would normally be ethane, right? Drop the E at OIC acid. Unfortunately, again, this has a common name. This is called acetic acid. This is called acetic acid, and we could see it like this as well. I guess I've seen it like this. It's kind of funny because when you're looking at an organic textbook or studying organic chemistry, this is primarily the way you see acetic acid. But when you're looking at intro chemistry or general chemistry, this is the way you see it. Remember a polyatomic ion, acetate? There it is, acetic acid. What's this one? Huh?
Butanoic acid.
Butanoic acid. That's not what you said the first time, though, is it? You said propanoic acid, because you didn't count that carbon in there. Yeah, it's 4. C4. Longest carbon chain, 1, 2, 3, 4. Butane. Drop the E at oic acid. This is butanoic acid. How about this?
5-chloro-pentanoic acid.
5-chloro. Anybody have 1-chloro? Nobody had 1-chloro, right? Because we number our chain with priority given to the functional group. Because of the requirements for the bonding in the carboxylic acid class, that is 2 oxygen to oxygen, 1 to OH, it only leaves 1 bond left on the carbon, which means the carbon of The carboxylic acid functional group will always be carbon number 1. You don't have to locate it. So this is always carbon 1, 5-chloro. I have 5 carbons, pentane, pentanoic acid. This is 5-chloro. 5-chloropentanoic acid. Notice the carboxylic acids, ic. They end in ic acid, or more specifically oic acid, and the word carboxylic acid ends in ic acid. All right, these little clues are going to help you on the exam because there are so many functional groups and so many naming protocols. Okay. There is an aromatic form, right? An aromatic form of the carboxylic acids. Which means it's got benzene in it, right? Never get that. What's that one? Benzoic acid. Yeah, you know how you know it? You memorize this. I mean, it's pretty close. Benzene, you know, and then you drop the E and add oic acid. It's not quite within our rules, but it's clearly pretty close. Benzoic acid, it's just an aromatic derivative of the carboxylic acid. Okay? Everybody good with that? Naming? It's pretty straightforward. I mean, these naming protocols, once you once you become a believer in them, then you understand the systematic approach, and you say, well, I just need to memorize this protocol for this functional group. Now, as the name suggests, carboxylic acids, these are acids. And when you put them in water, they ionize, they give up their proton. Now, these are weak acids, right? These are weak acids. They're organic acids. We refer to them as organic weak acids. Here's our carboxylic acid. Now, once it's deprotonated, it's termed carboxylate. Notice the ATE ending. This could also be in the form of, it also look like that. Now, the carboxylic acid functional group is the first time that we've encountered one of our groups that can actually change forms based on the pH of the local environment. And if the OH is if the proton is present versus the proton being missing, you have to indicate that in the name. So the carboxylic acid functional group can take two forms. Okay? One, it has the proton. The other, it does not. And this is relative, like I said, to the local pH of the environment. I think the pKa's for carboxyl groups can range somewhere around 2.1 to 2.9, somewhere around there, in terms of when those protons are lost. But memory serves me correct on protein amino acid ionization. I think that those pKa's for those are about 2.3 or 2.4, which means it loses the proton at a pH, at 3. pH 3, the proton will be gone. Okay? We have several examples of this. We just saw one a minute ago. This is acetic acid. If you put acetic acid in water, which we do, and that's vinegar, it's salad dressing, right? We get, let me get rid of this. Notice acetic acid, acetate, and this is the polyatomic ion that you memorized. C2H3O2. This is your acetate anion. I didn't remember write it in there. You have other examples. There's lactic acid, lactate, formic acid, formate. There's amino acids, glutamic acid, which becomes glutamate. There's aspartic acid and aspartate. There are several examples of this. Okay? And you just need to be aware that the deprotonated form of the carboxylic acid is called the carboxylate. Okay, you may see that somewhere. Wink, wink. Okay? Somewhere. Okay, everybody see it? This is there's going to be a lot of different types of reactions in this particular chapter, but you have to see the similarities so that you can learn the differences, and that's how you're going to know these particular types of reactions. Okay. Because this is an acid, it can react with bases in a class of reactions which we learned as neutralization reactions back in Unit 6 or 5 or whatever that was. It seems like such a long time ago, right? So we can react the acids with the bases. And if you keep this in mind, the carboxylate form, you'll see that there's pretty similar products. If I react this with a base, I'm going to do an example. So I'm going to give you the general reaction first. So this is it's neutralization. So we're going to have carboxylic acids. Plus a base. We'll see what our products are. Now before, when we reacted a carboxylic acid with water, the carboxylic acid was a proton donor. It donated H plus to the water, and the water became hydronium, which is what we always see when you donate a proton from an acid to water. And the conjugate base was carboxylate, the deprotonated form. So let's see what happens when we actually add, in this case, a base. I'm going to add NaOH. Notice we got where we have our carboxylate form. The carboxylic acid is still going to donate and it'll leave behind the carboxylate. The H is going to get with the OH here. This is kind of like a double replacement where sodium is replacing hydrogen. So we're going to get some water, right? But this, because it's a strong base, will ionize into Na+. The OH has already been taken up by the H+. So we have an Na floating around. It's floating around. This is an ionic bond. It's not covalent. That's why we don't show the line going across. This is an opposites attract type interaction. And that's what you're going to have with metals, right? Metals don't form covalent bonds. Metals form ionic bonds. This is the sodium salt of the carboxylic acid. Remember what a salt is. Take any acid you want, any acid, any acid. Take away the H+ and put something other than H+ there. You have a salt. Our most common one, there's HCl, there's the acid. I'm going to take away the hydrogen, and I'm going to put hydrogen ion, and I'm going to put anything else there. For us, the most common one is this. That's our salt. That's the common table salt. Okay? But any acid, okay, the anion of any acid with something other than hydrogen is a salt. This is clearly the anion of the acid, isn't it? It's the anion of this acid. Right here's the acid. I gave it to you. I lose H+, I create the anion. So, carboxylate is an anion of an acid. And it's combined with something other than hydrogen, which makes it a salt, by definition. I have a specific example. I use acetic acid. So we'll use acetic acid. And the only reason why I keep using acetic acid is because I don't want to write out those long carbon chains. It hurts my arm by the time this lecture's over. So we'll give it a little bit different look. We'll use it in the COOH form. We're going to add NaOH. And again, you could almost think of this as a double replacement. Here's a specific example, and the salt is really easy to name. And you kind of use something that you already know. You know this is sodium chloride, right? So when you name this, you just use the name of the cation, sodium, and then you put it with the name of the anion. The same thing here. This anion is acetate, that's sodium, so this is sodium acetate. Sodium acetate. Everybody see that? Carboxylic acids and carboxylates. They're just different forms of the same functional group. Any questions on that so far? All right. Esters. So another functional group are esters. Esters, the functional group for an ester is our carbonyl group again, C double bond O. And I'm going to put a prime on one of those R's, indicating that those alkyl groups don't have to be the same. They can be different. Okay? So we have a carbonyl carbon that's bound to an OR, not an OH. If this was an H, then it would be a carboxylic acid, right? But it's required that bound to that oxygen is at least one other carbon. Okay, so we know what alkyl groups are. Any of the alkanes minus one hydrogen. So there's any number of possibilities that can be attached there. And when you prepare esters, we'll do the preparation of esters before we do the naming, because the naming, at least how it's presented in the book, is directly related to how they're prepared. But I don't do it that way. I'll give you a real easy way to name the esters. The process that prepares esters is called esterification. Esterification, and this is the preparation of esters. It's preparation of esters. And you prepare esters by reacting carboxylic acids with alcohols. This is going to prepare esters. And it is a dehydration reaction, which means you're losing water. So we're going to have water as a product. It's dehydration. Put that little aside in here. It's dehydration. Now generally, we find esters to be quite pleasing, their odor. Okay? Depending on what carboxylic acid you mix with what alcohol, you can get different fragrances for esters. Things like, we actually do some in the lab, spearmint, wintergreen, bananas, pears. These things are all esters. And again, compared to most organic compounds, which we've smelled already, like formaldehyde and things like that, these we consider quite pleasing. So we'll do a generic one here, just with the functional group to begin with. Okay, so here's my carboxylic acid, and here is my alcohol. Remember when we looked at our alcohols that it's just an alkyl group attached to OH. It's our alcohol. We are going to dehydrate, so we're going to lose water, and it's going to come right here. It's a bit more complex than this, but at least for us, we can just say this is how we're going to lose water. And it gives us the correct orientation now to put this, what we call an alkoxy group on. Remember the alkoxy group from naming ethers? More complex ethers anyway? Methoxy, ethoxy. We're going to take this thing around. You see this oxygen? This oxygen has to connect at the same point that this oxygen's at. You can't just take this and stick it over here with the R group. The R group doesn't connect here. The oxygen has to come first. And then the sequence of whatever the alkyl group is follows. Usually it's going to be something like O, CH2, CH2, CH3, something along those lines. Yeah, this is acid catalyzed. Figured. It's acid catalyzed, which means we have to throw an acid in, get this thing going. And we're going to end up with our ester plus water. Now, this is a reversible reaction because the breakdown of esters is called hydrolysis. We're going to see that in just a minute. We're going to split this water into H and OH, and we're going to add OH back across here and H to the OR group to give it the alcohol functional group back. A specific example, I think they did one in the book, acetic acid and ethanol. Let's do acetic acid plus ethanol acetic acid plus ethanol. Everybody sees ethanol, I hope. Here's our water. Right? Then we have to connect here. That's where we're connecting. Plus water, of course. You see how I spun that group around? I didn't just take the alcohol R group here and just stick it right on. People will do that. It blows my mind. They'll stick the CH3 on here. Give their carbon 5 bonds. Go CH3, CH2O. Everybody see how to do those? Do a couple more because you're taking home Lab 9, just like you did Lab 4. This is what it is. All right, it's all test tubes with different carboxylic acids and different alcohols in it. So you're going to have a whole lot of fun, writing these things. All right, so let's try some more so everybody's comfortable with it. Again, I'm just writing H plus up there as a catalyst. Usually, you're looking at sulfuric acid. Sulfuric acid is usually the acid of choice to use as a catalyst in most reactions. What alcohol did I give you? What is it? Propyl? Isopropyl alcohol. Or if you ever get really confused and you don't really know, it's 1, 2, 3, right? 2 propanol. Right? That probably won't be a choice, though. I'm telling you right now on the exam, that probably won't be a choice. 2 propanol. Let's too easy. So what's this thing look like? We're going to draw in our structure of our carboxylic acid. There it is. I'm going to connect on my R group here. OR, right? O, CH, CH3, CH3. I'm just so used to using the Y form. Okay, we're going to lose our water. Here it is. Right, there's our water, and we're going to connect that O right here, that carbon. Everybody see that? It's kind of a tricky one because of where the oxygen is. It's a secondary alcohol, right? We've been doing primary alcohols up to this point. And you'll probably have all examples of primary alcohols in the lab exercise. Water. There it is. There's our OH. We're going to lose this H. That's gone. We're going to swing this oxygen around, and we're going to connect it right at that carbon. Now it's a little different because I gave you a different form of the carboxylic acid functional group, but same stuff. Now, when we're naming our esters, most protocols want you to identify the carboxylic acid and the alcohol. That's what most of them do. They say, oh, name your ester, find your carboxylic acid, take the oic acid ending, drop it, and add OATE. And then for the alcohol, name it by its alkyl group. Blah, 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 blah. Way too much there. There's a little easier way to name these. First of all, if you have an ester, you have an oxygen interrupting your carbon chain. Just like you saw with what? When's the only other time we saw our group, our carbon chain, interrupted with a heteroatom? The ethers. Very good. Very good. The ethers. If you have an ester, find the oxygen and draw a line through it. If you have an ester, you've just separated your molecule into two fragments. One of the fragments has a C double bond O. The other doesn't. And incidentally, there's nothing that says the C double bond O has to be on the left side of the oxygens or the right side. I think I've been writing them all on that side, but they don't have to be. I could write this one like this. See, there's nothing that says that the oxygen has to come on either side or whatever. These are the same esters. We'll show you. Find your oxygen, draw a line through it. If you have yourself an ester, you have a C double bond O containing fragment, a carbonyl containing fragment, and a simple alkyl fragment. Name the alkyl group normally. Propyl. I'll name it over here. Propyl. Name the carbonyl containing fragment by naming the alkane. How many carbons? 4. What's a normal 4-carbon alkane? Butane. Drop the E and add OATE. Oit. Name the alkyl group first. This, no matter which one you're looking at, is propyl butanoate. Propyl butanoate. Now, we're not going to see any substitutions on these groups. So you won't see chlorines and fluorines and stuff like that on these esters. I suppose they exist. I just haven't seen them. Okay, and when we come up with stuff, we don't just write things down just to write things down. We like to stay with actual molecules that actually exist. So, making things up out of our head. Okay, so it doesn't matter, which way the ester is. It's still propylbutane. What's this one? Huh? Ethyl.
Is it ethylene?
Methanoate, you said? Ethanoate? Yeah, if you draw your line through, right? What are you stuck with? Ethyl, and then the 2-carbon version, ethane, and drop the E, add OATE, ethanoate. Ethyl ethanoate, but no, it's common name here. C2H3O2, this is acetate. Remember the common name? So this is ethyl acetate. This right here is acetate. It's the deprotonated form of acetic acid. Okay? It's not an anion, but there it is. That's the one you memorized. That's the only kicker. I think that's the only one that you really have to keep an eye out for, because he uses that a lot. He likes that one. What's that? Good? What's this one? Yep. Ethyl, propane, ethyl propanoate. All right? What's the question? Yes, you do, Captain. What's the question? What?
Thank you.
So, you will have to see or name esters. But something else you'll have to do is you'll have to be able to determine, given an ester, what alcohol and or carboxylic acid was used to make that ester. So, let's say that we have an ester. Let's say we have us an ester, and I don't want you to name it. I want you to tell me what carboxylic acid was used to produce this ester. Now, we follow our same protocol, okay? These are give me questions on the exam. You can't afford to give these up because these are give me points. We do the same thing. We draw our line through the oxygen that is interrupting our continuous carbon chain. And we have two fragments, a carbonyl-containing fragment and an alkyl fragment. Well, if we're asked for the carboxylic acid, which one of these fragments do you think gave you the carboxylic acid, or came from the carboxylic acid? What's a carboxylic acid functional group look like? Right? See that? That had to come from the carboxylic acid. So, you need to pick your carbonyl containing fragment, the C double bond O fragment, and just name it using its carboxylic acid functional group. Use it for carboxylic acid name. So, how many carbons? 5. What is the C5 version of a carboxylic acid? Yep. Pentane-oic acid. Drop the E at OIC. Pentanoic acid is the carboxylic acid that had to be used to create this ester. What alcohol? The alcohol had to come from the other fragment, right? The alcohol had to come from the alkyl fragment. What is the C3 version of the alcohol bound at carbon 1? Propanol. You have one propanol. You could have propyl alcohol, a whole bunch. You're going to need to know how to do this. I promise. Okay? Does everybody understand? Everybody understand how to solve these? Let me do another one. Yeah. Oh, we all get it. But yeah. One more. Give me them both. I want to know carboxylic acid, and I also want to know the alcohol. What is it? Both of them.
Methanoic acid and 1-propanol.
1-propanol is good. What about the other one? I'm telling you. When I say something, years of experience, I'm telling you, don't forget about the carbonyl carbon. This is not methanoic acid. I see you erasing again. All right? What is this? Ethanoic acid, or no, that's the 8 form of it. What is it when it's got the hydrogen? Acetic acid, right? So here we go. We got this 1, 2, 3 bound at carbon 1. This is 1. Oh, it's the same one I used last time, huh? 1-propanol. This one here, ethanoic acid, right? But ethanoic acid is acetic acid. It's hardly ever called ethanoic acid. But if you're so struck dead set on IUPAC system, you're going to just go right through, which is what you should do. IUPAC, ethane, drop the E at OIC. That's what you want to do. But they have these ridiculous common names for some reason that are so prevalent that everybody's forced to accept them. Notice it's not acetate, right? Because we were asked for the carboxylic acid. If you were asked for the carboxylate that produced it, then you would say acetate. You see the difference? It's not hard, right? It's not hard. It's just a lot of stuff. It's not in and of itself, individually, these are not difficult. And when you're sitting here watching this lecture, you're like, oh, I know how to do this. This is cool. This is cool. But then you get home, and all of a sudden, things start jumbling together. So you got to make sure that you're comfortable with each functional group. You need to know the structure. You got to recognize the structure. You have to be able to name it. Okay? Well, we can break these down. We can break esters down into their carboxylic acids and their alcohols. And this process is called hydrolysis. And literally, hydrolysis is hydrolysis, water splitting. Okay? Hydrolysis, water splitting. That's what this means. Splitting water. Now, remember, esterification, the preparation of esters, is a dehydration process. We lose the water, right? We lose the OH off the carboxylic acid and the H off the alcohol to get water. Well, to break that, the opposite happens. We split the water into the OH and H, and we add them back across that bond and break that bond into the carboxylic acid and the alcohol. It's a reverse. So we'll have our ester here. Let's see, we'll do a generic term here for now. Here's our ester, and then we'll do a specific example. And I'm going to add water. This is acid catalyzed. This is acid catalyzed. Again, usually that's going to be H2SO4. Notice that it is reversible. We're going to think about our water being HOH. And we're going to get back our carboxylic acid. Plus our alcohol. We're going to split this water, right? And the H is going to go here. And the OH group is going to go back onto the carbonyl carbon. It doesn't, I mean, you need the catalyst, so there's things going on here before that. You're actually going to protonate this, make it a good leaving group, then the oxygen's going to attack and kick it off, and then the oxonium ion is going to deprotonate. So it is a couple of steps, and we don't care about them. But just know that the OH ends up back on the carbonyl, and the H ends up on the alcohol. The funny thing is that it's not this H that ends up here. It's one of these H's that ends up. I guess in the end it would actually be the H from water. H plus. Okay? Hydrolysis, splitting of water. Because we used an acid here, this is called acid catalyzed hydrolysis. This is acid catalyzed. Because guess what? We have a base, catalyzed one too. We have a base catalyzed hydrolysis as well. Base catalyzed hydrolysis of the ester. There it is. I'm going to use NaOH. Notice this one is not reversible. We're going to have some water in here, of course, we've got to have that to split. Notice again, this is the sodium salt. Alcohol. Notice with the base, you do not produce a carboxylic acid. You do not produce a carboxylic acid because you're in a basic environment. In a basic environment, it's going to be deprotonated to its carboxylate form. A little kicker. Okay, so two types of hydrolysis, and this is usually how it is. You can usually acid catalyze or base catalyze hydrolysis. And these are going to be breaking down processes, degrading processes. All right? Noticing the difference. One here is in equilibrium, one is. Okay. What's next? Amines. Amines. Amines are going to be organic derivatives of ammonia, which is NH3. They're going to be organic derivatives of ammonia, where 1, 2, or 3 of the hydrogens in ammonia are replaced with alkyl groups. You're going to replace these hydrogens with R groups, and the R groups could be aromatic. Okay, could be aromatic. Could be that phenyl group, that alkyl derivative of benzene. So we have ammonia. Now remember nitrogen. Nitrogen's in group 5 on our periodic table. Remember, we go all the way back to Lewis. Ammonia is in group 5, or nitrogen, sorry, is in group 5. Doesn't look much like an N. So I have 1, 2, 3, 4, 5. I have 5 electrons around ammonia, or nitrogen. Sorry. Which means nitrogen wants to form, bless you, 3 bonds and have 1 lone pair. Does everybody see that? So nitrogen is neutral with 3 bonds and 1 lone pair. Right? And we know where we got it. Nitrogen's in group number 5. What happens if we bring in an H+? Now, I'm just showing this aside before we get to primary and secondary tertiary. What if I bring in H+? Now, H+ is nothing more than a proton, right? And it's got a 1s orbital, but it's empty. Right? Because you remove the electrons. That's how you got H+. Right? If H+ comes into nitrogen and wants to form a bond with nitrogen, nitrogen will do it. But instead of normal bonding processes where each of the players brings in an electron, see, nitrogen's going to do it here. Okay? If it forms a bond with something else, it's bringing its own electron to the party. The other guy's bringing his electron, and then there's 2 electrons, it's covalent. But if you have a situation where nitrogen is going to form a bond with H+, and H+ doesn't have any electrons, what will happen is these guys will steal the electron. Both of the electrons from nitrogen are what? Are forming the bond. Okay? Now, if you look at nitrogen and you see that it forms its 4 bonds, it's still got 8 electrons. So its octet is good. But nitrogen is only entitled to half of those electrons, which means it's only entitled to 4. It wants 5, but it's only got 4 now, which means it takes a positive charge. It's 1 electron short from what it needs to be in order to be neutral. And we saw this with ammonium. Remember the ammonium ion that you memorized, NH4+? Now, the reason why I give you that little bit before we do primary, secondary, tertiary naming and everything like that is that most of the time when you see a nitrogen compound, any compound that contains nitrogen, your first thought should be base. It's basic, because most nitrogen-containing compounds are basic in nature because they will accept protons at the electron pair. So they're basic, right? And that's what we're going to see a whole lot of. We're going to see a whole lot of protons being added to nitrogens, and nitrogens taking positive charges and taking their names ammonium chloride, okay? But you already have some, you're familiar with that. This isn't something that should be completely unfamiliar to you, because you've seen NH4+, okay? All right. I'm hoping in a minute that that little thing makes what happens in a little bit a little easier. Okay, if we replace one of the hydrogens with an alkyl group, we get a primary amine, or amine. There's not any real stipulations on what this R group should be. It could be branched, it could be straight chain, it can be aromatic. There's no real requirement that says it's got to be within these parameters. It doesn't. Okay? And again, it doesn't matter which one I substitute. All of these hydrogens are equivalent. So, putting the R group here, I've just randomly chosen that hydrogen. I could have put it at any one. They're all the same. If you substitute 2, you get a secondary amine. And if you do 3, you get a tertiary amine. And I should include the dots here to be technically correct. I'll include the electrons. Usually you do see them written with nitrogens. It's funny because a lot of times you see oxygen, but they don't write the 2 pairs, lone pairs on oxygen. But they usually do with nitrogen. So you see those lone pairs. And just remember, that's just a consequence of it being in group 5. That's all it is. Okay, naming the amines is pretty straightforward. If you have an alkyl group substituted on the amine, you just name the alkyl group and attach the suffix amine to it. All right, so, for example, for a primary amine, you see the alkyl group right here? It's methyl. This is methylamine, all one word. It's methylamine. Or again, methylamine. Doesn't matter how you pronounce it. So for primary amines, and they're all really kind of handled the same. For secondary and tertiary, you have multiple alkyl groups. If it's the same, then you would go diethylamine or triethylamine. Or if they're different, we would alphabetize them. So we'll do some examples here. How about this? So on this particular one, you immediately see the nitrogen, you see one hydrogen there, which makes it a secondary amine. Because the other two, see how you have two hydrogens here? That means that, you should have three. But if you have two, then there's one R group on there. Primary. If you see one hydrogen, that means there's two R groups on there. So this is ethyl. You see one group here and one group there. Ethyl and methyl, I want to alphabetize them. Ethyl, methyl, amine. All one word. For the tertiaries, you can see them kind of funny. These are the same thing. See, that looks a little unusual, the NCH3,3. What is that one? Trimethylamine, right? Should be trimethylamine. Trimethylamine. Okay, so amine nomenclature, pretty straightforward. Pretty straightforward. Nothing really new there, right? The only word there is amine. You already know what the alkyl groups look like. You know what the characteristics of nitrogen are. So let's see how nitrogen behaves. A couple of reactions. Let's see what some of the basicity characteristics of amines are. We'll do with water first. So if we look at ammonia, if we use ammonia, and remember, amines are the organic derivatives of ammonia. So by learning just a basic characteristic reaction for how ammonia behaves, you could make a real good prediction and say, hey, I bet amines are just going to behave the exact same, except I'm going to remove 1, 2, or 3 hydrogens and put 1, 2, or 3 R groups on them. Right? That's exactly what we see. Let's see with water first. And we already did that one up there with water. We'll do with acid here in a minute. And I'm going to pick a primary amine because that is the one that Siri picked. So I'm just going to take some primary amine. And I'm putting the positive over the nitrogen because that's where it is. It's the nitrogen that's actually positive. I didn't do it quite. This is ammonium ion that you guys memorized. So I put it there because that's how it shows in your book. But notice the similarities here. NH2, R, NH3. R, NH3 instead of NH4. If you simply substitute a hydrogen in for the R group, you have this exact reaction. Example. Methylamine. This is a methyl ammonium ion. Notice this up here was ammonium, right? That's ammonium. We just took away hydrogen, put a methyl group in it, so it's methyl ammonium. Now these are bases, so they will react with acids. So here I did with water, here I'm going to do with acid. I'm going to pick the same one. Add HCl to it. This is not reversible, sorry. This is not reversible. I'm going to add my proton, and I'm going to get the same ion I had up here. But this time, I have a chloride ion hanging around. Yes?
Since it's a base and an acid, would that be considered neutral?
Yeah. Yeah, it's acid base. This would be our methyl ammonium chloride. It's our methyl ammonium chloride. I think that's another. Yeah, take that one. Yes?
I think the NH is supposed to be NH3.
You're right. Thank you. Just saw that at the same time you. So they're similar, right? I mean, the nitrogens are basic at the lone pair. They will accept protons at their lone pair. And when they do, they become electron deficient species. That's why they take these overall positive charges. Okay? The two primary mechanisms or two primary reactions involving nitrogens as bases are when you have the proton donor being water and when you have the proton donor being any of a number of different acids. But you can obviously see the similarities. You can see the similarities in the reactions. Okay? Okay, last one. Are the amides. Amides is our last functional group. Now, when you have an amide linkage, you have a carbonyl, C double bond O. One of your bonds from the carbonyl carbon has to be to a nitrogen. Okay? A lot of people look at this and say this is a carboxylic acid, where the OH was substituted with an NH2. This is a primary amide. Okay, because you have only a single substitution alkyl group here. You do have nitrogens, or two hydrogens that are on the nitrogen, and it is possible to substitute R groups on that nitrogen. So you can have and I'm going to put an R prime on that, indicating that these two do not have to be the same. And then if all of those hydrogens are substituted, I'll put a double prime on one and a single prime on the other. Now, they can be the same. They can be the same alkyl groups. They just don't have to be. Okay, there's no requirement that says they have to be. Okay, when we're naming amides, we have to separate out a protocol for primary versus amides that have substitutions at the nitrogens. Okay, and we'll see how to differentiate that. But if you have a primary amide, you're going to drop the E from the alkane parent and add the suffix amide. Suffix amide, so it's going to be all one word. When you have a primary amide, you're going to have a hydrocarbon chain attached to your functional group. So you're just going to have an alkyl group attached right here. One, two, three carbons makes that a propane, right? Drop the E. Propanamide. There is a C1 version, unfortunately. What do you think that one is? It is. How did you? Are you guessing?
No, because I remember the other ones when there was an H and another group.
Yeah, normally this would be one carbon, right? So, oops. Normally we'd have one carbon. We call that methane. Drop the E, methanamide. But it's almost exclusively named by its common name, formamide. Notice again that C1 version, taking that forma prefix, formaldehyde, formic acid, formamide, C1. There's a C2 version, of course. What's that one? Yeah, cetamide, right? Normally we would say ethane, ethanamide, but almost exclusively known as acetamide. Acetamide. There's that aceta for the C2. The only thing we had with that C2 derivative being aceta is it's not right with the ketone because it's actually acetone is a C3, right? First one. Just keep that in mind. Other than those first two, which are by now expected, the nomenclature amides, primary amides, pretty straightforward. You can substitute on them, okay? You don't see that a whole lot, but it's possible. Because of the requirements of the amide functional group, we know that there's only one other connection point. So we don't have to locate it. 1, 2, 3. This will be 3-chloro. Propanamide. We don't see too many of them, but I just want you to know that they exist. For secondary and tertiary amides, we indicate the substituted groups on the nitrogen with a capital N before the name of the substitution. So for secondary and tertiaries, notice here we have a methyl. Right? The methyl is on the nitrogen of the amide group. So this would be N-methyl. N-methyl butanamide. All one word. See how I located that methyl group? And that's different if I had a methyl group here, for example. Then I would just say 2-methyl-butanol. Right? If the substitutions are located in this chain, we just use our similar 1, 2, 3, 4, whatever to locate it. But if it's on the nitrogen, we have to do it. Secondary. You could have an ethyl there, and it would be an ethyl. We can have two groups. Can both be substituted, of course. In the case of two groups, you still indicate that both of them are on the nitrogen by preceding each substitution with the capital N, but you alphabetize them. So here's ethyl, right? That's an ethyl, so I would have N-ethyl, N-methyl, butanamide. They're getting longer. Okay, so primary amides, just name them. Parent chain, drop in the E, add suffix amide. Secondary and tertiary, alphabetize N-substituted alkyl groups. Indicate that they're on the N with the capital N. Okay, last thing. So last thing. Hydrolysis of amides. So we have acid and base catalyzed hydrolysis. So we can hydrolyze we know what hydrolysis is. We're going to split some water. Taking a quick look, our acid hydrolysis produces a carboxylic acid and the ammonium. And our base produces a carboxylate, our sodium salt. So this is pretty consistent with the reactions we've been dealing with up to this point. So under acid conditions, acid catalyzed, we'll have a generic here we have a secondary amide, right? And we're going to add heat. That means heat. That little delta is a generic term for heat. I know these are getting uglier and uglier and uglier and uglier. They are. Carboxylic acid. Okay, again, we're acid catalyzed. We're going to split water, right? We're going to split water. Normally, when we hydrolyze these linkages, our OH is going to go to the carbon. That's why we get our carboxylic acid. And these guys are all going to go to the nitrogen. So you see 1, 2, one of those, where'd the OH go? Hold on. 3, 4, 3. Oh, it's acid catalyzed, so the H plus has to stay there. So out of these 4 hydrogens, we have 1, 2, 3, 4. Because it's acid catalyzed, there still has to be H plus floating around. That's why there's only 3 used up over. That would be our ammonium chloride and carboxylic acid. So specific example, we have one. The ammonium chloride. That would be ammonium chloride. We're using acetamide here. For our acid hydrolysis, yeah? This is the last part of the organic. I know there's a lot. 2 more reactions, that's all we have. Base catalyzed hydrolysis. Notice all of our base catalyzed, we never produce the carboxylic acid. We're always producing the sodium salt. We are consistent here. There's the sodium salt of what would be our carboxylic acid. That's RNH2. Let's see, it's prime. That's a prime. And I'm differentiating these R groups here by putting the R. This should be R prime up here. I don't want you. These 2 groups can be the same or not, but regardless, this one is the one that ends up with the nitrogen, and the first one is the one that ends up with the carboxylic acid. Again, using acetamide. Plus sodium hydroxide and a little heat. Notice with the acetamide we produce the sodium acetate, which is the salt. And ammonia. There's a lot to learn here. Okay, I would learn them all as acid catalyzed or base catalyzed. You see, we had acid catalyzed or acid hydrolysis in each one of those. I would keep them all together and clump them up and learn them that way, because I know it looks like a lot, but it's really not. Once you start studying, you're going to start to see these consistencies that arise. I know you're all saying, no, I don't believe you. And I think by and large, there's not an expectation, at least from me, that you know every single portion of every single reaction. Just know them kind of qualitatively. Remember, it is a multiple choice exam. So you might see a question like something along the lines that says, the reaction that produces a silver mirror is called blank. And then you would just say tolerance test, right? Like I said, my expectation is not that you'd be able to write that whole entire reaction. Or you might have something that says, you know, base catalyzed hydrolysis of amides produces ammonia. You know, something along those lines. So I don't think that, you know, you need to go through and hardcore memorize every single thing. You do need to know something. I mean, you need to know that, you know, the addition reactions for the alkenes, you know, oxidation of primary, secondary, tertiary alcohols, qualitatively kind of what these are, you know, ammonia, for example. I'm not going to ask you to spit these reactions up on an exam, okay? But there are certain ones that you need to know. Okay, remember, I think when we started, we're done. We're done with all the material for the next exam. And I think that you know, out of all the reactions, 8 or 10 of them, that's what you need to, you know. I'm not going to tell you which 8 or 10. Okay, so that's it. We'll start biochem tomorrow. Biochem will be a little different. Everything will be done on the PowerPoint. So the molecules are just too big.